want to really understand what was going on, what was the state of the matter at that time. But let's see this evolution in a better detail. What do we mean creating the Big Bang or creating the early stage of the universe? So if you see, so from the Big Bang, there is such kind of an evolution up to now, as I said, something like 14, maybe 15, or even more billions of years. But what we want to understand is what was going on here in this stage. So when all the particles before the nuclei, so protons, neutrons, and all the other particles, were formed. We are talking about something like 10 to the minus 4, 10 to the minus 6 seconds after the Big Bang. As we will see in a few slides, there was a state of matter called quark-gluon plasma. This is what we want to recreate in the laboratory. Let me already say that the temperature that we want to create here is 10 to 13 degrees. So we are talking about something like, let's say, 2,000 billions of degrees in the laboratory. Imagine that the temperature of the sun is 15 millions. So there are several orders of magnitude of the matter we want to create in the lab, just if you compare to the matter of the sun, the matter of a star. So the evolution of the universe is more or less the following. So we are here, let's say 15, I said 14, but it's the same, billions of years. So everything now is what we know, and we know that the temperature of the universe is around 3 degrees Kelvin. And if we want to investigate the universe now, we are in the field of astrophysics. If you want to understand what was going on something like 1 billion of years after the Big Bang, so when all the massive galaxies and so on were created, we are in the field of, let's say, biology, because here also all the chemical of the hydrogen was formed, the carbon hydrogen, and the temperature of the universe, the average temperature, was 18 degrees. If we are in the chemistry field, it means that we want to study the nuclei when they were formed, so something like 300,000 years after the Big Bang. But if you want to stay in the nuclear physics and subnuclear physics, that's what we are going to investigate today, we are in this range, so up to 1 minute from the Big Bang, going down to something like 10 to the minus 34. And in this range is the quark-gluon plasma that I mentioned before, when the temperature is, again, something like 10 to 15, 10 to 12 degrees. Then there is another stage, let's say the one very close to the Big Bang, up to 10 to the minus 43 seconds from the Big Bang. This is the range of cosmology, but we are not touching this field. So why we want to create this stage? First of all, we want to, as I said, create the initial condition, the universe, because at that time, we had all the possible particles created. What does it mean? It means that all these particles are carrying or carried information. But these particles, usually, they decay. They decay in a fraction of a second. And just after this fraction of a second, all the information are lost, because we don't have any more these particles. So what we want to do is to recreate these particles and to understand, to take back the information that was at the beginning of the universe. So this is, I guess it's clear that the basic information that is behind this study. What to do? How to create the particles, how to create this early stage of the universe. We can use accelerators. So this formula, I guess, if you're here, you know this formula. E, it's in some way equal to the mass. So this is the basic idea that is in an accelerator. We take mass, for instance, 2 protons, or an electron and anti-electron. So these are mass, known mass. We accelerate this mass at very high energy, and we collide these 2 particles. So from this part of this side of the formula, we go to the left side of the formula. So mass and mass, we create energy, pure energy. Then from this energy, we go back on the right side, and we create mass. But this mass now is a new mass. It's not the previous electron, or proton that we knew before. Now we have the new particles. So we are creating the new particles that we had at the beginning of the universe. So going from here to here and vice versa, this is, again, the idea of an accelerator. The first accelerator has been built here in Frascati. I guess you will go around in the lab, and you will see. This is just close to the entrance, and was made by this guy here, Bruno Touschek, here in the 59. It's called ADA, Anello di Accumulazione. Then it was built Adone, a large ADA, under the cupola that maybe you saw the way. So this was working until the 90s. And then Adone was replaced by Daphne, that is the machine that is here into this cupola, the dome. And let's say this is the largest accelerator ever built. So starting from that idea, from the idea of ADA, this is LHC, Large Hadron Collider at CERN, that is working since 2009. So it's a 27 kilometers ring, 100 meters below the surface. This is just a draw, of course. You can imagine this is 100 meters below. This is the Laboratori. This is CERN. And these are all the other accelerators that are needed to inject and to run all the particles into this accelerator. Just as a comparison, you see this is the airport of Geneva. Now, so this it's an idea that started something like 20 years ago, because the first idea of LHC is from the 84, so 30 years ago, but then there was a gap. So at the beginning of the 90s, it was approved, and all the construction, the experimentation and construction started. So this idea really took something like 20 years to start up. This is the tunnel that I mentioned before. We will see something better later. So this was during the construction. You see this is a hall that will host the experiment. This is one of the 1,200 dipoles that are forming the accelerator. And this is the final tunnel, so 27 kilometers here. You can imagine how intensive the energy of these particles inside. The particles, they do 11,000 turns per second. So 27 kilometers, the particles, they do 11,000 times per second and collide in the places that we have the accelerators. This is the accelerator control room, so it's a kind of flower. You see, it's 1, 2, 3, 4, and each desk has some specific task, of course. Science is getting more and more global. These are all the nations participating to the project. The blue ones are the member state, like Italy. You can find your country here. These are member state, means they are the owner of the experiment, the owner of the laboratory. All the others, including USA or Russia, they are not member. They are participating, but they are not the owner of the experiment. So you can imagine something like 6,000 plus 3 plus 1. So something like 10,000 physicists, engineers, technicians are working in this project. And what is really interesting, I guess for you, this is something really interesting, is the distribution of the age. So you see the average of the scientists, or let's say PhD students working at CERN is 26. So this is really nice because this means that there is a really young community. And then there is a long tail up to the retirement as somebody that is also 85 maybe. So this is what I said. This is the accelerator. And there are 4 experiments in these accelerators. There is LHCb, Atlas, CMS, and ALICE is the one that is that I'm going to mention today, because ALICE is the experiment that is dedicated to this kind of study, so to investigate the matter at the beginning of the universe. You can imagine that here there is some detail, but let's say all the accelerator weighs something like 40,000 tons, and everything is at the temperature of the superfluid helium, so around 2 Kelvin, 2 degrees Kelvin. So this is the, if you remember the plot I showed before, that the temperature of the universe is 3 Kelvin. So you can imagine this is the coldest point in the universe, because it's 1.9 Kelvin only. And for instance, this is Atlas, one of the 4 experiments. This is the largest one. You can imagine this is the size of a person. You see here, you see here. So you go down by a lift of 100 meters, you open the door, and you find this huge cathedral just in front of you. Alice, this is another picture. Again, this was during the construction. This is a man. So this is the tunnel. This is the place where the beam is coming in this direction. Another is coming in the other direction. But we enter in the details in a second. And this is some picture from ALICE. ALICE is the 2nd largest experiment. You see a man here, and this is the huge magnet that it's then filled with all the detectors to identify the particles produced. This is the LHC tunnel during the construction. So you see here the beam is coming in this direction, another beam is coming in that direction, and they collide in the center of the experiment. So, but let's do some step now. This was a kind of introduction. So we know, I guess, I don't know if Catalina before showed you something, which are the bricks of the universe. Before studying the matter that was there at the beginning of the universe, we had to understand the bricks. And the bricks are given by the standard model. I guess this was mentioned before. And this is the standard model. So this is, let's say, a table that you should take in your pocket. When you about the universe, you take your sheet of paper and say, okay, this is what I'm formed, or the universe is formed of these particles. So we have 6 quarks. Quarks, the name, of course, are fantasy names. Yeah? Up, down, charm, strange, top, and bottom. And all these quarks are the bricks which are forming the hadrons. So all the particles that are not elementary. Protons, for instance, are formed of 2 up and 1 down. Neutrons are formed by 2 down and 1 up. I don't know, K plus is formed by 1 up and 1 anti-strange. And so you can you do all the possible combination, and you will have all the particles that are in the universe. Then there are leptons. Leptons are more, let's say, aristocratic particles because they don't mix each other, they stay alone. Electron, you know, it's just rotating around the nuclei in an atom with a neutrino, electron, neutrino. Then we have a muon neutrino, and tau neutrino. All these particles are called fermions, are the bricks of the matter. Fermions because they follow the statistics of Fermi-Dirac, and they are called fermions. Then we have these other particles, gluon, photon, and these 2 bosons, They are the mediators of the forces. They are the responsible the forces. We will see in a second all the forces. And they are called bosons because they followed the statistics of Bose-Dirac. And this is why the name boson. Then, in addition, there is another guy, I guess you heard before. There will be a talk, I guess, tomorrow in a couple of days. So yeah, I don't enter in all these details. And this is called Higgs boson. Again, it's a boson. And this particle is a kind of director in all this scheme. But again, I will not mention these things because somebody will do later on. And then we have all the forces. We have the gravitational force. Let's say this is a strength 1, just to give you a strength. The weak force that, okay, it's called weak, but it's 10 to the 29 times the gravitational force. Then there is an electromagnetic force that is 10 to 40. This is the electromagnetic, perfectly. The mediator is the photon, while here before the mediator for the weak force is the boson W and Z. And then finally the strong, that is of course the strongest one, is 10 to the 43 times the gravitational force. That it's the force that keeps together the nuclei, for instance, all the particles together. I said before we have up quark, down quark together. Who is keeping these particles together? The strong force, and the mediator is the gluon. Good. Now we are to the Big Bang. Again, this is another way to see all the evolution. We are more or less here. What was going on at that time? So what we have to do? So we had to create a mini bang in the laboratory. If we collide, as I said you before, an electron and an anti-electron, or a proton and antiproton, unfortunately, this is not enough. Why this is not enough? Because they can create single particles. The Higgs boson, for instance, was created, investigated, or let's say investigated, making a proton-proton collision. But in this case, you are producing the single particle. You are producing the bricks. What we want to do is to recreate a mini bang. We want to have really, as I wrote here, a chunk of matter, yeah? Something that I want to study. I want to really see what was going on there at the first stage of the universe. So just 2 single particles are not enough. Then, but my system cannot be just a chunk of matter that I put somewhere, because it must be accelerated. It must be accelerated to ultra-relativistic spin, so something really close to the speed of the light. And also this chunk of matter must follow all the thermodynamics rules that are there. They were there at the early stage of the universe. So what we can use heavy ions. We can use ions, so we take an atom of lead, that is one of the heaviest element, stable element. We can scratch, we can take out all the electrons, and we remain just with the nuclei of the lead. The size is 10 to minus 14 meters, so it's really tiny, but it's large enough to simulate or to recreate the early stage of the universe. Then, at that time, at this moment, we can really, in this finite volume, we can do all the study that we want. We can see how it evolves. We can see the temperature. We can see the flow. We can study all this chunk of matter. And what is the name of this new state of matter is called quark-gluon plasma. So it's a plasma. We will see later what is that. And quark-gluon, I mentioned you before. So you know what is a quark. it's a brick of the matter. You know what is a gluon. Gluon is one of the mediators of the strong force, the force that is forming, is keeping together the particles. Correct? Are you following me? So if you have some problem, just stop me, ask, so I can explain again, go back. So don't wait the end of the talk. So these are the two ions. Let's see if they start. So we take these two ions and collide together. You see, they are coming, and they produce the new particles. All these guys are particles produced in the collision. Let me show you again. See, coming, interacting, and producing. So here, they already, I mean, we are already far away from the early stage of the universe. You can imagine that the stage, the real matter, is just only when they interact. Once you see the single particles, you are already out of the system. The particles are already produced, and you can study each single particle. You can understand what was going on in the interaction. Have a also look to the time. This is, let's say, more or less nanoseconds. So this is billions of seconds. So this is what we have to investigate. So we are more or less 7, 10, 20 nanoseconds. This is the time scale that we have to investigate. And now I have a question for you. I said we take nuclei. And in our mind, nuclei are more or less a sphere, round. But here, you see two disks going on. So is it a mistake, or there is some idea? Perfect. So we have already a master degree physicist. Good. So he catch the trick. Is not a trick. I mean, they are, as I said, they are really going fast. They are really close to the speed of the light. They are ultra-relativistic atoms. And due to the contraction of the space, you know, the relativity, Einstein relativity, so in the direction of the speed, there is a contraction of the space. And indeed, they are disks. They are not anymore a sphere, but there is a contraction, and they appear really like two disks. Let me show this. So this is what is interacting. We have two disks interacting, and then we have the production of particles. OK. After that, we arrive to Alice. So this is, I show you before some picture. This is the beam. So the ions are coming here, other are coming here. Then they collide here. So there is a collision each 25 nanoseconds. Each 25 nanoseconds, we have a collision, new particles produced. We record all the information that are going on. And then again, after 25 nanoseconds, new collision, and so on. This is going on continuously. And we, of course, collect all this data. And at a certain point, of course, we have to analyze. So offline, we analyze all this data. All these pieces that you see here are different detectors. Each detector is meant for something. There is this central part that does the tracking. So when a particle is produced and going into this detector is leaving a track. Then it goes here, and here we measure the time that needs to go from here, because we identify the different particles by time. And then the particle arrives here, and here there is the calorimeter to measure the energy of the particles. So you can imagine each part here is able to identify some characteristic of the particle. So the charge, the energy, the momentum, which kind of particles, and so on. And studying all this information, we can understand what was going on in the interaction, what was going on when we formed this chunk of matter. Something like 1,300 physicists are working in this experiment, so from 100 institutes, 30 countries. And this is another simulation where you can better see what I just described you here. So this is below the ground. You see the ground is up on the 100 meters above. So this is the accelerator. The two bunch, because they travel in bunch, these particles are arriving. They collide here, you see, in the center. And in the center, you have all the particles produced. Each line is a new particle that is traveling into the detector. You see, and here all these detectors are able to make the work I told you before. Also have a look to the time. Again, we have to do this in all these tiny fraction of, so something like 20 nanoseconds. Let me just run another time. So as I said, the particles are not traveling alone, but they are bunched. So they are a bunch of particles traveling, and for each interaction, usually we have one interaction. So for each bunch interaction, we have only one particle interacting. You see here? These are a lot of other small detectors here, close to the interaction point. So this is the fireball, and when you see all the particles, as I said, we are already out of the early stage universe, of the universe. So only in that region, in something like 1-2 nanoseconds, we have 2,000 billions of degrees formed. Okay? And then is the state of matter that we want to understand. Okay, let's go ahead. So we formed, so in this region, we know that the universe was formed by a kind of soup. I will explain you why it's a soup. Soup made of quarks and gluon, called quark-gluon plasma. So I can mention briefly why we want to study this, but it's clear we want to understand the universe with the early stage of the universe, and if it's really possible to get these degrees, 2,000 billions, if we compare to the temperature of the sun. Of course, as I told you before, the size of the system is 10 to the minus 14 meters. So it's really tiny, of course. The sun has some other size, of course. Now, this is something difficult. Okay, but if you already understood the relativity, I guess you will not have any problem, as everybody of you. But let's say this is something not easy, but it's worth to mention. I want to introduce you this comment. This is called asymptotic freedom. In 2005, 3 guys got the Nobel Prize for explaining these things. I told you that protons are made of quarks. For instance, this is a proton. 2 ups, 2 quark up, and 1 quark down. And they are free. What does it mean? That they don't feel the interaction among each other. Yeah? If you can imagine that they are confined in a cage. So if you are in a cage, you cannot escape. But inside the cage, you are more or less free. Why this? Consider the Coulomb force, so 2 charged particles. What do you know? You know that if they are far away, the force you feel is, so 2 magnets. Yeah? Take 2 magnets. You know, if they are far away, you don't feel so much strength. But if you really are right together and close by, you really feel a strong force. Yeah? If they're far away, you don't feel anything. If they're close, you feel a strong force. And this is the potential of the Coulomb force. So far away, the potential is really low, close to 0. If you are really close, you feel a strong force. In elementary particle theory, the QCD, this is the quantum chromodynamics, you have an opposite behavior. So when you are really close by, you don't feel any force. But if you go far away, you feel a strong force, even stronger than this, because it goes like an exponential. So you can imagine now what was going on here. If they're close by, you are here, you don't feel any force. But if you try to catch the d quark, for instance, and take out from the cage, the energy, the force of this interaction increases a lot, and you are not able. You're really like a spring. Yeah? You feel a force when you try to take out this guy. But what is going on here now? If I try to separate two quarks, as I said, there is a strong force, a strong energy between these two gluons. But this energy, at a certain point, is able to form new particles. Is it clear, the concept? Suppose that I have one particle that weighs 5, another particle, antiparticles, that weighs 5. I try to separate these two particles. At a certain point, the energy inside, between these two, is equal to 10. So it's able to form two particles with 5 plus 5. I said this is not clear and something easy to understand, but this is the reality. And this is the concept of hadronization. So if I have two quarks, for instance, in my interaction, I have two quarks. At a certain point, I try to separate these two. There is a force here, an energy, able to form other two quarks. At a certain point, they stop, and then they glue together to form other particles. So I will never be able to have a single quark, because as soon as I try to separate, I will form new particles. Is it clear, this concept? This is not an easy concept. It's called asymptotic freedom, this one. Then the confinement, because they are confined in a kind of cage. And if I try to separate, I go to the hadronization. So why I introduced you this phenomena? Because this is what we have to do. So this is the problem that we have to face when we try to create the early stage of the universe. Because we know that at a certain point in the universe there were hadrons. But if you remember this fireball expanding, this is after the creation of the universe, the creation of the particles. We have to arrive to this quark-gluon plasma, that it's a soup of quarks and gluons with no hadrons. So they have to stay all together. They really to stay confined, so in a kind of soup, so free to stay, to go around, but not separated. Because if you try to separate, you already produce an hadron. So this is the second phase. First phase, everything is free to stay in the soup. So, is it clear? Not really. What is not clear? Some question? Okay, think about this. Maybe at the end we will go back. So, as I said, this thing was clarified in a theory, and in 2005, these three guys, Gross, Politzer, and Wilczek, got the Nobel Prize, and they really say that during the Nobel lecture, Gross said that before understanding the quark-gluon plasma, it was able to go back in the time something like not before 200,000 years from the Big Bang. So to understand what was present before, so all the dynamics of the universe, we had to really form a quark-gluon plasma. And this is what we made in Alice. We do. But let's now do another step. You know that the normal phase, the phase of the normal matter is this one. If you take a water, you know that there is a ice, the solid, there is a liquid, there is a gas. Then there is a fourth state. This is a plasma. Plasma is, for instance, the sparks, magnetic strong fields, aurora, the neon. And so this is the plasma. So fully deconfined state. And this is the same diagram for the universe, for the matter. So here you put the energy, the temperature if you want. This is the number of particles produced. And this is our world. More or less we are here. Nuclei, hadrons, hadron gas, nucleon gas, blah, blah, blah. Then there is a quark-gluon plasma that here. The early universe is here. It's really up, very high temperature, no particles, because I said it's a soup. And LHC works here. LHC, so Alice and LHC are more or less here. Quark-gluon plasma, very high energy. Then on the other side, there is a neutron star, and so on. So understanding all these phase diagram, we really understand the evolution of the universe, all the phases of the universe. So where can we produce the quark-gluon plasma? OK, this is clear. We are talking, it's 1 hour that we are talking about this. Big Bang, but this already happened, so it's gone. Then there is a lattice QCD. Lattice QCD is a simulation. So by simulation, it's possible really to recreate these things, but it's a simulation. It's a computer simulation. So we are putting into all the information we have. And of course, if you have wrong information or we don't have enough information, our knowledge is not so deep. But anyway, this was a good starting point from the 80s, more or less, to study the early stage of the universe. Also, this happens in the neutron stars. If you remember the plot I showed you before, there is a corner with the neutron stars. It's possible to understand the QGP phase there. But so more or less, we have one event every 300 years. So we don't want to wait so long. And then LHC, that is what I showed you before. So this is the event that I showed you before. So you can imagine that each line is a particle produced. We have these, so we have thousands of these particles, each 25 nanoseconds. So each 25 nanoseconds, we have to register, we have to store all the information of each single particle and then to analyze it. This is a problem. This is a problem because we have a huge amount of data. Data, you cannot imagine how large are these computer centers, but there isn't any computer in the world able to analyze this data. Single computer, I mean. What we developed was the grid architecture. I'll tell you in a second. For instance, just the quantity of data produced is 1.3 gigabytes per second. So it's per second we produce 6 times the Britannic Encyclopedia, for instance. This is per second. If we want to put on CD this data, each year we pile up something like 20 kilometers of CD. Of course, we don't do, but okay, if we had to store this. So as I said, we developed the grid. What is grid is a architecture that connects all the computers, of course, working on this project in the world. When in my office, on my desk, I run a code to analyze data, my run suddenly breaks in 100 pieces. Each single piece goes to, I don't know, to Tokyo, to New York, somewhere, I don't know. That detector analyzes the single tiny piece, and when it's ready, comes back in my computer. Only in this way it's possible to analyze the huge amount of data. Otherwise, we would not be able to do what I showed you before. Then, so we said, so I said, we want to go back and produce the early stage of the universe. But maybe we are producing some black hole too. You know, there was, I don't know if you followed, when LHC started, there was somebody screaming, saying that we are going to destroy the universe and the world because we are going to produce a black hole. Is it possible to produce a black hole in the universe, at the LHC? So this picture said it's black, it looks like a hole. I say it's a black hole. It's not really like that, but let's say we can produce mini black holes. These mini black holes are really tiny. Let's say the cosmic black holes are usually 3 times, they start from the size of 3 times the solar masses. We are producing something that is 10 to the minus 14 meters, so really different. And very hot, very hot. So it's, right, this is the energy, tera electron volt. Okay, I don't enter these details, but they're really hot. And there is a theory by Hawking saying that these tiny black holes, they evaporate. So they are not stable. As soon as they are created, they evaporate in other particles. Up to now, we didn't see any mini black hole. Maybe we will produce it, or them, but anyway, this is a possibility that is not, of course, dangerous at all, but it will be interesting to add other information to the early stage of the universe. Can we produce a real black hole, huge, that will eat all universe? This is not possible because you see the scales here. This is a cosmic black hole. Needs 10 to the 19 giga-electron volt. So this is the energy. And at LHC, we have 10 to the 4th. So there are something like 15 orders of magnitudes. So one with 15 zero after of difference between these two. So it will never be possible to produce any stable cosmic black hole. Anyway, if we will produce something, this is the signature of a black hole. So you will, this is the interaction, and these are all the particles produced. So this is simulation, will appear like this. But for the moment, we didn't see anything like this. So this is a soup rich of information. Of course, they are all technical aspects, something that, I mean, it's not for this masterclass. But anyway, you can imagine that by all these things that we are studying, we understood, we really are now understanding the early stage of the universe. Just to mention you something, this is a list of observables that are not or less interesting for you because are, how to say, professional information. But this is something maybe that is interesting to know, that the early universe was a perfect fluid. So it behaved really like a perfect fluid. It was not a gas. As I told you, it's a kind of soup But this soup was a perfect soup following the hydrodynamic laws of perfect liquids. Okay, we are more or less at the end. So I introduced you Alice and LHC, and both are really operating wonderfully, unveiling these first secrets of the early universe. And I've also explained you the connection with the black holes, the connection with the grids, so the problematics of the data acquisition. So this is really in a strong connection with other branches of physics that are really intriguing and interesting. But before ending, I take you another minute to also, I'm sure that Gino Isidori, I guess tomorrow, will talk about this. But in case, just to give you, to scare you a bit, because we are in a dangerous life. So what we understood that our universe sits in a not stable situation. So measuring the Higgs mass, we know that it was measured a couple of years ago, that it's 126 GeV here, and knowing the mass of the top quark is, you remember the plot, the chart I showed you before, the universe sits here. So it's not in the complete stability. It's not unstable at all, otherwise it will not be here, but sits in this meta-stability. This is a zoom. You see, we are more or less here. What does it mean? We sit on a ground state that is not completely stable, but we could have a transition at a certain point, maybe now, maybe tomorrow, maybe in 20 billions of years. This we don't know. For sure, it lasted these 15 billions of years, that because we are here. I mean, there was a complete evolution. But at a certain point, this universe will make a transition to another ground state. And this will happen at a certain point. I guess it will take time. But this is another point that we understood in our study of the early universe. So just concluding, this was a conclusion that Fermi said after a conference like the one that I gave today. He said, I'm still confused, but at a very high level. OK, thank you. Good. Now, so we have time for questions, I guess 5 minutes before Simone starts his talk. Questions? Don't be scared. We are not going to make transition now. Yeah. So there is a ground state. A ground state means the lowest possible energy that you have. This everywhere. It's like in an atom. So the possible energy you have. Let's say this ground, this floor, this is the ground energy, energy zero. In the universe, this ground energy sits on a metastable, so it's not stable, completely stable. You can imagine this floor completely flat. You can move everywhere, and it's stable. But this ground state universe is not stable enough. At a certain point, maybe we will have a transition to another ground state, like another floor, let's say. We will move to, and the universe will change completely, of course, because having a different ground state will reassemble in a different way. But this we don't know. I mean, we don't know the details. We don't know when this will happen. So you understood everything about confinement and quark-gluon plasma. Yes?
Concerning the confinement, like you said that we can't really separate two quarks because as soon as we do that, two other particles are created as well, and those two initial quarks get one of those two particles.
Perfect. Yes.
So what happens if we try to separate those two new particles?
the same. It will continue. Let's say, let's take this. Exactly. So if you continue this, of course, you can you will have other particles and then another combination that this is the way you have all this incredible flux of particles. So you can imagine if here the energy is really strong, I mean, you put a lot of energy. If you do this by a small accelerator, yeah? You do this collision using a small accelerator. So here the energy is few, you can maybe have something like this, only 2 particles. But if you put here a lot of energy, like an energy of LHC, you can continue this process for a lot of these steps, not 10, but maybe 1,000, and in each step you have new particles. This is why at a certain point, as I showed you before, you will have thousands of particles. Everything is coming from a single interaction, but then you have a shower of these particles, because the energy is so high that you have to, when you stop, when the energy here is not enough to produce new particles. So it's the opposite. It's not when you give energy, but it will stop when the energy is not enough. So at LHC, the energy is so high that you continue this sequence until your energy is not enough to produce new particles. And then you see that you have thousands of particles at the end. Yes.
Transition from energy to particles, right?
Exactly. Is the formula that I showed at the beginning, E equal mc.
Does it happen simultaneously, or do we produce it in the...
Simultaneously or what? I mean...
The transition from third to fourth particle.
No, it's not simultaneous. No, it takes time. I mean, the scale, time scale is the one that I showed before. So we are at the time of, I don't know, nanoseconds, from 2 to 3 to 4. Okay, here we should enter in this quantum mechanics.
But is it spontaneous? Does it happen by itself? Or
by itself, no, by itself. Yes. I mean, here there are a lot of conservation laws, of course. Why we have always 2, why we have always a quark and anti-quark, there are a lot of conservation laws. Also from here to here, you have a lot of conservation laws going in.
I also remember when you were talking about the forces and there was 4 of them. And
there was, for example, that gluons are the ones responsible for the
strong
force, and then photons and W and Z bosons.
Yes.
But
gravity. There is no gravity here, you see? Because this is a problem. I mean, this is a challenge. What does it mean that we have these mediators here? It means that we were able to describe the force using the quantum mechanic theory. So the modern approach to the physics. Unfortunately, for the gravitational force, there is no quantum mechanic theory. So we are still not at the Newton level, but at the relativity, this general relativity and so on, that is not a quantified, not written in the quantum mechanic language. So this is why we are not able to put here a mediator, because we don't know if there is a mediator, which kind of mediator we have. There is just a name, it's a graviton. There should be a mediator of the gravity force, but we are still in the process to write the quantum mechanics expression of the gravity. So Einstein working on this for decades, other theorists working on this for up to now. I mean, but for the moment, there are problems that are not yet fixed, solved, to put the gravity into this more modern, let's say, framework, like for the other forces. Last.
Just wanted to ask if detecting the gravitational waves will bring us any closer to graviton?
Right. Let's say in the, well, will not help in writing the quantum mechanic form of the gravitational, but detecting a gravitational wave will say that the general relativity is correct. I mean, we are on the correct path. If we don't detect any gravitational wave, and let's say it doesn't exist, because it doesn't mean that if you don't detect it doesn't exist. If it doesn't exist a gravitational wave, this means that we have even more problem on the gravitational force. But let's say these two problems are a bit disentangled. I mean, it's detecting a gravitational wave doesn't mean that we will be able to put gravitational into quantum mechanics formulation. It's more a theoretical problem. It's not an experimental problem. Last question, if you have? No? OK. So I stop here. Enjoy your masterclass. Here we move to Simone, that is busy writing a message. OK. Okay, thank you. Sì, devo questo.